Welcome to CSC 201, lesson 6.1. Apologize that I'm recording this video with a little bit of a cold. It's not going to sound pleasant. Okay, so recall the following from chapter 1. A set can be thought of intuitively as a collection of elements. If A and B are sets, then A is called a subset of B, written A, that I read that as contained in B. If and only if every element of A is also an element of B. That is, A contained in B means that for every element X, if X is in A, then X is in B. And A is not contained in B means that A is not a subset of B, so there is at least one element X such that X is in A and X is not in B. If A and B are sets, A is a proper subset of B, if and only if A is contained in B, but A does not equal B. That is, for every element of A is in B, but there is at least one element of B that is not in A. And we often denote this as this contained in symbol without the equal sign beneath it. So we say A strictly contained in B. Venn diagrams are a useful way of visualizing sets and subsets. So here I have a picture of A contained in B. So we have a large B with A fully contained within it. So this is a picture of A as a proper subset of B. And this is a picture of A equal to B. So you still can say A is contained in B if you use the little equal sign underneath, contained in or equal to B. So you draw B, and then you could draw A as the exact same thing. So we still say A is contained in B, and when in fact they are equal. And then some pictures where A is not contained in B. They could be two disjoint sets, nothing in common. They could be two sets where they have some in common, but there are some elements of A that are not in B. And it could be that B is contained in A, but there are elements of A that are not in B, which means that A is not fully contained in B. Okay, so this is called the element argument. It's the basic method for proving that one set is a subset of another. So we let sets X and Y be given to prove that X is contained in Y. First, suppose that X is a particular but arbitrarily chosen element of capital X. So we have one element of this capital X here, and we need to prove or show that little x is also an element of Y. For example, suppose that A is the set of all integers such that n equals 4p for some p and z. Okay, so we are going to say A is the set of all multiples of 4. Okay, so this says the set of all n and z such that n is a multiple of 4. So let's list these out a little bit. So we've got -4. If I just do roster method, 0, 4, 8, 12, 16, etc. All the multiples of 4. And then set B is going to be the set of all n and z such that n equals 2 times q, where q is an element of z. So these are multiples of 2. So if I list multiples of 2, I would have -4, -2, 0, 2, 4, 6, 8, 10, etc. I should put ... dots on the left too. Okay, so I want to prove that A is contained in B, that every element of A appears in B. So we can see like -4 is in A, it also appears in B. 4 is in A, it also appears in B. 8 is in A, it also appears in B. 12 is in A, it would be the next element that I did not write in B. Okay, so to prove this, we choose a arbitrary element from set A. So we let X be an element of set A. We need to show that X is also in B. Okay, so that's our goal here. Let's just be explicit about that. We need to show that X is an element of B as well. Okay. All right, so if X is in A, that means that for some p in the integers, x equals 4p. That's the definition of what it means to be in A. But 4p could be written as 2 times 2p. And 2p is also an integer, because adding and multiplying integers gives you integers. Okay, so since 2p is an element of the integers, x, which is 2 times 2p, is a multiple of 2. And that's the definition of being included in set B. So therefore, x is an element of B. So A is contained in B. So that's the element method of proof. You choose an arbitrary element of A. We need to show that that same element is in B. So we let x be in A. That means that it equals 4p, which is 2 times 2p, which means that x is a multiple of 2. Therefore, x is an element of B. So every x that's in A must also be in B. So A is contained in B. All right, we want to disprove that B is contained in A. So looking at the elements of B, we're trying to disprove that every element of B also appears in A. So to disprove a for every statement that every element of B also appears in A, you just need one counterexample. So I just need to find one element of B that is not in A, and we have disproven that B is contained in A. So how about 6? 6 appears in B, but it does not appear in A. So 6 is an element of B, but 6 is not an element of A. So B is not contained in A. All right, to prove that two sets are equal, you have to show two things, okay? A equals B is typically proved by showing that A is contained in B and B is contained in A. If every element of A is also in B and every element of B is also in A, then the two sets are equal. So suppose that A is the set of all m in Z such that m equals 3 times an integer. So we're looking at multiples of 3 for A. And then B, we're looking at the set of all n in Z such that n equals 3b minus 3 for some b in Z. So we want to prove that these two sets are equal. These are just different ways of expressing or describing the same set. So it's a two-step process. We need to prove that A is contained in B and B is contained in A. So step 1, we want to prove A is contained in B. So to do that, we let x be a random element of A, which means that x equals 3a for some A and Z. So for some, oops, I'm going to do a little a. For some A in the integers, x equals 3a. Which can be rewritten as 3a plus 3 minus 3, right? So you can add and subtract the same number. That's still the same value, 3a. And then from these first two elements here, I could factor out a 3, and I would get a plus 1, and then I still have the minus 3. And a plus 1 is an integer. since a plus 1 is an element of the integers, let b equal a plus 1, and we have x equals 3b minus 3. 3 times an integer minus 3, where b is an integer. And that's the definition of containment in set B. So, right, set B was 3b minus 3. So, x must also live in set B. Therefore, x is an element of set B. So, A is contained in B. Okay, step 2, we have to prove it in reverse. Prove that B is contained in A. So we let x be an element of B. Then x equals 3b minus 3 for some b in the integers. Thus, x equals 3b minus 3, which can be rewritten by factoring out the 3, and you get b minus 1. And b minus 1 is an integer. We'll just rename it a. And we have that x equals 3a, which is the definition for membership of set A. Therefore, x is an element of set A. So A is contained in B. So finally, we say by 1 and 2, A equals B, right? In part 1, we showed A was contained in B. In part 2, oops, I did it back. I wrote it backwards over here. We concluded x is in A. We assumed x was in B. We concluded x was in A, so B is contained in A. There we go. Okay, so we proved that A is contained in B. We proved that B is contained in A. So by those 2 steps, we conclude A equals B. We're going to define some operations on sets. We have 4 for today. We have union, intersection, difference, and complement. So the union of 2 sets, A and B, is the set of all elements that are in at least one of A and B. So I think of the word, just like little memory trick I use for this, union, I think of like marriage is a union. And so you're marrying everything together from 2 sets. Pull everything from A and everything from B into one big set, the union. Intersection, which we denote with this upside down U. So the U represents union, the upside down U represents intersection. And this is the set of all elements that are in common to both A and B. I think of it as the intersection of 2 roads, and the intersection is that square of road that's actually common to your 2 roads that are intersecting. So if you drew a picture of it, right, 2 roads intersecting would look like this. And that's the intersection. It's the part that's common to both roads. So A intersect B is the set of all x in the universal set, such that x is in A and x is in B. So union is an or, intersection is an and. The universal set U is just like the world that A and B live in. So it's just this big set out here. All right, the difference between 2 sets, that's the set of all elements that are in B but not A. So it's the set of all x in the universal set. such that X is in B and X is not in A. So as a picture, we say all the X is in B, but take away the elements that were in A. And then the complement of a set is the set of all elements in the universal set, in the universe, that are not in A. So we have the whole universal set, but take away the things that are in A. Okay, so for example, let's let the universal set be A, B, C, D, E, F, G. A is the set A, C, E, G. B is D, E, F, G. And I want to calculate the union of A and B, the intersection of A and B, B minus A, and A complement. So it might be helpful to draw a picture. So I have my universal set, and then A and B. I need to draw this a little bit bigger. Okay. So A has A, C, E, and G, and B has D, E, F, and G. So things that A and B have in common are E and G. E and G. So E and G go in the intersection. Let's call this one A and this one B. That's the big universal. Okay, and then A, in addition to E and G, also has A and C, and B has D and F. And is that all the letters in the universal? No, there is B missing. C, D, E, F, G. So there's a B outside here that's not in either A or B. Okay, so now let's figure out what's in the union. A union B is just marry the two sets together. Everything that's in A or B would be A, C, D, E, F, and G. Again, they don't have to be in any particular order. I was just doing alphabetical because that's what I'm used to. Okay, A intersect B. The elements that A and B have in common are just E and G. B minus A, so all the elements that are in B, but take away the elements that are in A. So we have all the elements of B, but subtract out, like carve out these ones that are also in A. So we're just left with D and F. And then A complement are all the elements in the universal set that are not in A. So I want anything listed in the universal set, but carve out things that are in A. So get rid of all of A. What's left is B, D, and F. Okay, so we'll do a similar kind of question, but instead of discrete elements, now we're going to have intervals on a number line. So set A is the interval from -1 to 0. So I'm going to draw that. So let's see, -1 to 0. This is set A. And then set B, I'm going to draw on a separate number line, but directly underneath so you can see how they line up. B goes from 0 to +1. This is set B. Okay, so I need to know the union, which is marry the two together. So if it's in A or it's in B, it's in the union. So that means I'm going to go from -1 all the way to 1 for the union. -1 to 1. Should I include the endpoints? Well, -1 is not in A, and it's not in B for sure, so I'm not going to include it in the union. It's not in A or B, so it's not in the union. So we put a round bracket, and then same thing with 1. And then A intersect B. Oops. That's any elements that the two sets have in common. And looking at this picture, it looks like 0 is the only thing they have in common, because 0 is in A because of the square bracket, and 0 is in B because of the square bracket. So that's the only point these two sets have in common is the point 0. So it's just one number, 0. And then B minus A is everything in B, take away anything that is in A. So here's all of B, right? The only thing that it shares with A is the 0, so I have to take the 0 out of B. So that would be 0 to 1, but this time I'm not going to include the 0 because the 0 is in A and I'm taking anything from A out of B. And then A complement is the universal set, which they told us in this case was the real numbers, the whole real number line, minus anything that's in A. Okay, so A complement is the set of all x's in the reals such that x is not an element of A. So let's see, that would be everything like out here and out here. So I would say it's negative infinity up to -1. And should I include the -1 in the complement? Well, -1 is not in A because of the round bracket, which means that it is in the complement. And then I need to union that with 0 to infinity. Should I include the 0? Well, 0 is in A, which means it's not in the complement. So I'm not going to include the 0. And like that. Okay, definition. Two sets are called disjoint if and only if they have no elements in common. That is, A and B are disjoint if and only if A intersect B is the empty set. And that's what this symbol means, this like 0 with a line through it. That's called the empty set. Nothing in common. All right, so let's look at sets 1, 3, 5 and 2, 4, 6. Are they disjoint? A and B, are they disjoint? Do they have any elements in common? Nope. Then yes, they are disjoint. So A intersect B is the empty set. They have no elements in common. So you can either put the curly brackets with nothing inside. That indicates the empty set. You can also use the circle with the line through it. Empty set. So are they disjoint? Yes. Okay, so to expand on that a little bit, you can have multiple sets, A1, A2, A3, as many as you want. And to say they are mutually disjoint, that would mean that no two sets have elements in common. So you'd have to check every single pair. Every possible pair of two sets would need to have nothing in common. So here I have 3 sets, A, B, and C. And I have to check every possible pairing. I need to look at A intersect B, A intersect C, and B intersect C. So those are all the possible ways that I can intersect 2 of the 3 sets. And if they are all empty intersections, then we say these 3 sets are mutually disjoint. So A intersect B. A and B, do they have anything in common? No, so we say that's the empty set. And then A intersected with C, 3, 5, and 2, nothing in common, so A intersect C is empty. And then B intersect C, 1, 4, 6, and 2, nothing in common. Their intersection is empty. So are they mutually disjoint? Yes. All right, let D be 2, 4, 6, E be 3, 7, and F be 4, 5. Are D, E, and F mutually disjoint? So we would have to check everything. D intersect E, D intersect F, and E intersect F. So D intersect E, 2, 4, 6, and 3, 7, that's empty. D intersect F, 2, 4, 6, and 4, 5. They have a 4 in common. D and F have a 4 in common. So this intersection is 4. And I don't even need to check the last one. If I find any set of 2 that are not disjoint, where their intersection is not empty, then the 3, D, E, and F, are not mutually disjoint. They have to all be empty to say that the 3 are mutually disjoint. Okay, to partition a set A is to break it into mutually disjoint subsets, so no 2 overlap. Mutually disjoint means no 2 overlap. So break it into subsets where no 2 overlap, such that the union of all the subsets is the whole original set. So this is an example of a partition. So I had a big set A, and I broke it into 4 subsets, A1, A2, A3, and A4. None of the 4 subsets overlap, and when I put them all together into a union, I get the original set A. Okay, so if I have A is 1, 2, 3, 4, 5, 6, I want to partition it into 3 subsets. There are many possible answers. So I could say A1 is 1, 2. A2 can be 3, 4. And A3 would be 5, 6. Okay, so all 3 of these sets are mutually disjoint. None of them overlap at all. And when you union them together, you get all of A. So another possibility would be that A1 could be 1, 2, 3. A2 could be 4 and 5. And A3 could be 6. Okay, again, none of them overlap. Union them together, you get the whole set A. So that's called a partition of a set A.